For what feels like forever, quantum computing has been pure science fiction. An impossible machine, always just 10 years away. The biggest hurdle? A single devastating problem. Quantum states are incredibly fragile. Imagine trying to build a house of cards on a speeding train. The slightest vibration or the smallest change in temperature could wipe everything out in an instant. This problem is called decoherence, and it is the final boss that has kept quantum computing locked away in research labs. But 2026 is shaping up to be a critical turning point. While the world has been obsessed with AI, a quiet revolution has been building in labs across the globe. The barrier of quantum error correction is no longer just a theory. We are seeing it become an engineering reality. This shift is kicking off a gold rush for a new kind of tech talent. And for B.Tech graduates, this is the signal to get in on the ground floor of what could become a trillion-dollar industry. Here's why 2026 is a year to watch for quantum computing. To get why this moment is so important, we first have to understand the kind of problems that have stumped even our most powerful supercomputers. Imagine trying to design a new life-saving drug. You need to simulate how a complex molecule will behave. A single protein can have more possible configurations than there are atoms in the universe. A classical computer sees the world in bits of zeros and ones. It is like a librarian trying to find a specific sentence in a library the size of a galaxy by reading every single book, one by one. It's not just slow, it's a fundamentally intractable task. And it's not just medicine. The same wall applies to creating new materials for carbon capture or designing hyper-efficient batteries. We've hit a ceiling. This is where quantum computers come in, and they play by a completely different set of rules. Instead of classical bits, a quantum computer uses qubits. Thanks to a principle called superposition, a qubit can be both a 0 and a 1 at the same time. Like a spinning coin that's neither heads nor tails, but a mix of both. When you link these qubits through a wild property called entanglement, they become a single, powerful unit. Instead of the librarian checking every book, the quantum computer can read the entire library all at once. It's like having a god's eye view of a massive maze, seeing every possible path simultaneously instead of exploring each dead end one by one. But here's the catch. This incredible power comes at a cost. That spinning coin, our qubit, is as delicate as a soap bubble. Any interaction with the outside world, what scientists call noise, can make it pop. It collapses into a boring classical 0 or 1. This is decoherence, the villain of our story. For years, the more qubits you added, the more fragile soap bubbles you had, making the computer less reliable, not more. The dream was trapped by its own fragility. So, what's starting to change? In short, the conversation has shifted from just building more qubits to building better qubits. The industry is entering what some are calling the fault-tolerant foundation era. And the key to this is quantum error correction, or QEC. Think of QEC as a team of digital bodyguards for our fragile qubits. Instead of relying on one delicate soap bubble, engineers use a group of them to form a single, much more robust logical qubit. It's like an orchestra. Trying to hold one perfect note on a single violin is extremely difficult. The slightest waver ruins it. But when an entire orchestra plays that same note, if one violin goes slightly out of tune, the collective sound of the group masks the error. The overall note stays pure and stable. The physical qubits are the individual violins, constantly checking each other. If one gets knocked off course by noise, the others spot the error, correct it, and save the precious quantum information. For years, this was mostly theory, but now it's becoming an engineering discipline. Companies like Google, IBM, and Quantinuum have all been hitting major milestones. Google's Willow chip proved it could achieve below threshold error correction. In our orchestra analogy, this means they proved that adding more violins actually made the overall note more stable and in tune, not just louder. This was a game-changing moment, turning a scientific hope into a measurable engineering fact. Now, we're seeing a race to build machines with more of these powerful logical qubits. In early 2026, it was reported that QuEra computing hit a world record, demonstrating up to 96 logical qubits. Meanwhile, Quantinuum showed off incredible efficiency, creating 48 logical qubits from just 98 physical ones. One thing worth being careful about: you will see much bigger numbers than these quoted online. Some of them count errors that were detected, not corrected. And those are not the same milestone. This isn't just about small lab experiments anymore. It's about building the foundational blocks for computers that can solve real world problems. It signals the beginning of the transition out of the noisy, intermediate scale quantum era, NISQ, and toward the age of fault tolerant machines. So, what does this actually mean for you? This engineering driven shift is creating a massive demand for a new type of talent, one that sits at the intersection of computer science, physics, and engineering. The good news: you no longer need a PhD in theoretical physics to join the quantum revolution. As the industry moves from pure research to actually building and running these machines, some of the most accessible jobs are in engineering and software. Companies are desperately searching for 4 roles in particular. Quantum software engineers are the architects building the bridges, the tools, compilers, and cloud platforms that let developers access quantum hardware. They're writing code in Python, using specialized frameworks like IBM's Qiskit or Google's Cirq. Quantum systems engineers are the mission controllers. They sit at the crucial interface between the quantum hardware and the software stack, making sure the entire system runs smoothly. Post-quantum cryptography specialists. Even before fault-tolerant machines are widespread, the threat they pose to modern encryption is very real. Companies are racing to build digital locks for a world with quantum keys. And quantum machine learning engineers, a hot emerging field that combines the exploratory power of quantum computing with AI to find patterns classical machines could never see. The job market is already heating up and is projected to grow rapidly. Major players like IBM, Google, Microsoft, Amazon, and Nvidia are pouring huge investments into their quantum divisions, and a whole ecosystem of startups is emerging. Salaries are reflecting this demand, with experienced quantum software engineers and algorithm developers earning well into 6 figures. Those are US dollars in US based roles. Indian salaries do not track that number, and you should not plan around it. What does transfer is the shortage. There are far more of these roles than people who can fill them. For B.Tech students in India, the opportunity is even more pronounced. India's National Quantum Mission, a government initiative backed by over 6,000 crore rupees, is rapidly building a domestic quantum ecosystem. This isn't just a research project. It's a national strategy to build a quantum-ready workforce. We're already seeing this happen on the ground, with new quantum courses and specializations popping up in universities. This educational push is creating clear, accessible pathways into the field. If you're a student right now, you are in a prime position to get in on the ground floor. Here are the essential skills you should focus on building. 1. The mathematical foundation. A strong grasp of linear algebra, probability, and statistics is non-negotiable. It's the language of quantum mechanics. 2. Programming proficiency. Python is the undisputed king of quantum programming. Get comfortable with it and then dive into a quantum software stack like IBM's Qiskit. 3. Core quantum concepts. You don't need to be a physicist, but you do need to understand the basics of quantum mechanics, algorithms, and data structures. 4. Hands-on experience. Thanks to cloud platforms from IBM, Google, and others, you can run algorithms on real quantum computers right from your laptop. One of the most powerful steps you can take is to enroll in one of the many online courses. The NPTEL course on quantum computing, created in a partnership between IIT Madras and IBM, has become a great entry point for students across India. It formalizes a path into this deep tech field. We are at a rare inflection point in history. The transition from theoretical quantum science to practical quantum engineering is happening now. Recent breakthroughs in tackling the error problem are beginning to unlock the door to a new era of computation. For decades, we've been limited by the binary world of classical computers. But the challenges of our time, from climate change and incurable diseases to global financial instability, are not binary problems. They are complex, multifaceted problems that require a new way of thinking. Quantum computing offers us that new way. The gold rush is just beginning. The companies that will define the 21st century are being built today. And they need engineers, developers, and problem solvers who can think in a new dimension. For B.Tech graduates, this isn't just another career path. It's a chance to help define the future. The question is no longer if quantum computing will change things, but whether you'll be ready when it does. If this journey into the quantum realm sparked your curiosity, like this video and subscribe for more deep dives into the technologies shaping our world. What part of the quantum revolution are you most excited about? Let me know in the comments below.